Let's start by framing a manufacturing problem, that is the collecting and storing of shop floor data. We've been doing this for years now with acceptable results. The approach usually is the following. Manufacturing data is collected at the equipment. Events are also being produced by IoT devices that collect relevant process information such as temperatures, humidity, and particles. This information arrives continuously or in bursts. Depending on your data collection capabilities, you might extract this information, send it to the MES, analyze it using custom applications, and create actionable insights so that you can dispose your production materials, maintain your machines, or even fine-tune product parameters. This usually involves custom development of specific applications and being very careful about the volume of information by selecting what matters and what's really not that important. What we often experience is that just to be safe, we store all information, even if we do not consider it relevant. We store it with the context data that comes from the equipment or the IoT device. This often leads to big relational databases that start small but quickly become a nightmare to maintain and offer poor performance. When we try to control these databases, we often need to throw away data or keep it for a short period of time. Another way to solve this problem is to develop ETL processes that try to merge relevant incoming data. This opens more possibilities, such as reporting and monitoring. We now face three problems. The first one is that ETL processes must be custom-coded and mostly around generic information. It also depends on what information is available and when. An ETL process takes time to complete, and finally, when the results are available, it's often relevant for medium or long-term decisions and almost never for real-time actions. Depending on your manufacturing process, yesterday might be a long time ago. The second one is the scaling problem. Relational databases don't scale very well. When having performance issues, we either tune the underlying codes, or when this is not an option, we add more hardware. We start by increasing memory, expecting the problem to go away. Then we try disk, and then CPU. Finally, we have nowhere to go unless we buy new hardware. Of course, we can divide data across multiple physical servers, but this only shifts the problem. The third challenge is storing unstructured data. It's quite common that manufacturing machines generate binary results, such as photos, wafer maps, or X-rays. Although unstructured, this information is important for process control. Sometimes the equipment vendor offers ways to analyze data, by, for example, using a pattern recognition software. Or we must find ways to store and give context to this information. This often requires a lot of effort and leads to one-of-a-kind solution. That being said, it was clear for us that we needed a new perspective in order to solve these problems. This new approach must be able to collect, store, analyze, and derive insights to improve business processes. All of this must be aligned with the vision of the factory of the future and the new challenges Industry 4.0 creates. Being IoT such a hot topic, there are several data platforms already in the market. So why do we need a new one? MES and IoT solutions coexist but rarely exchange data in real time. IoT and MES context information is available, very powerful, but difficult to correlate and often used in isolation. This way of using information only leverages a subset of possibilities. Just imagine how powerful IoT data becomes when enriched with MES context, or even MES data merged with IoT events. Joining MES and IoT data is in fact the way to go, and this is the challenge IoT Data Platform solves. By building a data processing pipeline capable of ingesting, brokering, processing, and serving manufacturing events, we can accommodate different workloads. This pipeline is composed of multiple layers, each one responsible for a specific function. The first layer is the ingestion. It guarantees authentication, consistency, and stamps each event with a timestamp and other system information. The next layer is the brokering. Here we store the events to disk. The broker also allows the next layer to fetch messages. This is one of the components that allows us to scale horizontally. The processing layer is responsible for treating the newly arrived events. This is where aggregation, automatic decisions, and intelligence takes place. In the processing layer, one event can create a new one, for example, a standard deviation of a process parameter. This can be used by another process app or passed to the next layer. Finally, the serving layer delivers events for visualization, can trigger alarms, or even write to a relational database. So, what are the main key features of this architecture? Firstly, it scales massively. By using well-established software solutions like Apache Kafka and Spark, we built horizontal scale at our core. This allows the system to grow when necessary or shrink if this is the case. We built a solution that can handle both structured and unstructured data. We can upload binary files to the platform and generate events that contain reference to that data. By building specific sinkers, we can store data in a relational database, providing tabular access for third-party tools. Because we can stream events through all the layers, we support online and offline operations. An offline operation can be a training of a machine learning algorithm. An online operation can be the triggering of an action based on the arrival of an event. We can support not only Connect IoT as a data provider, but also other event producers such as ERP, MES or PLM systems. The platform also supports the enrichment of events. This means that we can add extra MES information to any arriving event and then correlate it for reporting, monitoring, and analytics. Last but not least, we have achieved a low TCO. We do not require expensive hardware to enable high availability, as this is guaranteed by the architecture itself. Let's now see the platform in better detail. The ingestion layer is where the data providers send the events to. These events are then stored to disk. The brokering layer allows the next layer, the processing layer, to consume events at will. This is where the fun begins. The processing layer can divide the workloads into different kinds, stream or batch. We will see in a minute what this means. The results of these processing modes can then be routed to the previous layer or the next one, the serving output. This final layer is responsible for exposing the results using sinks, triggers or alarms. As we now know, the processing layer can accommodate two types of workloads. The first workload is batch processing. A batch process is when we need to aggregate information over a specific period of time, let's say a day or a week. Examples of these workloads are data warehouse aggregation jobs, data mining, and machine learning processes. Usually, a batch will contain millions of records and takes time to complete. For example, a machine learning algorithm can process all the historical data of a specific equipment maintenance event and then use it to train a predictive maintenance model. But now, when we need to quickly react to an event, batch processing will not help us. This is where stream processing comes into play. A stream is just like a never-ending sequence of records. By using micro-batch processes that run, for example, every 2 seconds, we can build processing pipelines and use that information to create an if this then that rule to trigger reactions, or we can use the predictive maintenance model that was trained in the batch process as a real-time remaining useful life indicator for a manufacturing equipment. One other stream processing app is the MES Data Enricher. It adds MES context to the incoming events in real time. Now let's bring these stream and batch processing definitions to the data platform architecture. We can now see that the processing layer already has clear examples of batch and streaming workloads. You have the example of the machine learning app that uses a batch process to train a model and then uses that same model within a streaming app to make a prediction. We have also the MES Data Enricher. This process will receive newly arrived events in real time and adds MES context information. If the raw event of an equipment only contains the material name, by using MES information, the enricher can add product details, production step parameters, or any other MES information related to the original event. The raw event now becomes an enriched version of itself. By merging IoT and MES worlds, the enricher performs one of the most important tasks of this platform. Let's expand the architecture a bit more. We now see the MES on top as an event producer. We also see the metadata registry as part of the ingestion layer. This is necessary because we need to know the schema of the arriving event in order to validate consistency and process it. We have examples of the serving layer. You can sync events to CSV or JSON files. You can send the results of a batch aggregation to a relational database so that third-party tools, just like Power BI or Tableau, can read the results. By creating a workflow, you can trigger alarms, an MES action, like putting a lot on hold, or call an API of an external application. Data scientists can use notebooks such as Zeppelin or Jupyter to connect to our platform and test algorithms. To summarize, let's see some use cases for the IoT Data Platform. The immediate use of this platform can be a simple storage of an IoT data for later analysis. We've also seen that by using SQL syncs, we can stream any event in real time to a relational database. The results can then be used by third-party applications. You can also define a workflow to monitor a specific sensor and, if the value exceeds a threshold, trigger an email notification, stop an equipment, and schedule a maintenance activity. Using historical data to train a machine learning algorithm, you can deploy the model as part of a streaming application and react in real time to incoming events with intelligence. For more complex manufacturing scenarios, you can process equipment results in real time and adjust process parameters directly in the MES for the processed material or on the same equipment for the next material. The possibilities are endless. Thank you so much. I will leave you with a small video to help you visualize what I've just said.
Manufacturers generate, collect and store huge amounts of data, but most cannot harness the insights to create value. To become relevant and actionable, data has to be refined, standardized and enriched with manufacturing contextual information for deep analysis. Generic IoT platforms alone cannot deliver the results manufacturers need. That's why Critical Manufacturing has created the first combined MES and IoT data platform. The Critical Manufacturing IoT Data Platform combines relevant data from your machines and edge devices with MES information and other data sources and processes all data in the context of manufacturing. As a result, manufacturers can make better decisions. As a natural extension of MES, the Critical Manufacturing IoT Data Platform framework consists of 5 main elements. Edge processing, shared with the MES platform, solves the challenges of data latency, high cost and security when compared to processing data in the cloud. The ingestion layer checks and stores data from all incoming sources, understands its manufacturing relevance and makes it available for processing downstream. The platform unifies all types of data in an MES-based common data model. Leveraging the latest Apache Kafka distributed event streaming platform, real-time data is delivered to downstream applications for processing. The IoT data platform handles both batch and stream processing, utilizing Apache Spark, a unified analytics engine for large-scale data processing, which supports a wide range of workloads. Data is enriched with MES contextual data, enabling more informed analysis, machine learning, and other AI technologies to create predictive models. Finally, the enriched data is made available through the serving and output layer. Any third-party applications for engineers and data scientists can access results, along with MES analytics tools to close the loop on actionable insights. Critical Manufacturing's IoT data platform leverages the power of data to monitor, manage, and optimize your manufacturing processes. Now you can gain the full benefits of Industry 4.0 and transform your manufacturing sites into smart factories. Seize competitive advantage with the power of data. Join the manufacturing data revolution with Critical Manufacturing.